Hey everybody, this is for our differential equations class, and yet it's not really a lecture about differential equations. It's a lecture about simple integration tricks. And the first thing that we're going to look at is integrals of composite functions whose inner functions are linear. Now, if we're not going to talk about differential equations in this lecture, why do we have this lecture for differential equations class? And the reason is, in our solution of differential equations, we always end up having to integrate something. And sometimes the things that we integrate can be a lot simpler than they appear. The things that we have to integrate may be composite functions. And when we integrate a composite function, we use U-Substitution, which means that we identify what U is, and then we compute du, and take part of the integrand and identify that as being a constant multiple of du, and so forth and so on. And most of the time when we integrate composite functions, that's the way to go. The exception might be is if we have a composite function whose inner function is linear. In other words, y equals mx plus b, a linear function, some constant times x plus another constant. And the thing is, if we are integrating such a function, we don't have to use U-Substitution because there's a trick that always works, and we're going to look at that. Note here that the linear function is of the form y equals mx plus b, and that the derivative of the inner function is just m, the constant coefficient of x. Now, let's take a look and see what would happen if we did use U-Substitution. For example, let's say that we have the integral of cosine of mx plus b. M is a constant, b is a constant. Well, we look at that thing and we say, this is the cosine of u. U equals mx plus b. Du dx equals m. Du equals m dx. And we look at the rest of the integral here, and all we have is dx. So we take this equation right down here and divide by m, or multiply by 1 over m, to get dx. And dx is the same as 1 over m du. And we take this constant 1 over m and move it out in front of the integral sign. And we integrate, and we get 1m sine of u plus c, or 1 over m sine of mx plus b plus c. And let's write down our result. Whoops. We study this result, and we realized what we did. We took the antiderivative of the outer function and got sine. We kept the inner function. And we just divided by the derivative of the inner function, 1 over m. And there's an analogy that we can make if we're computing the derivative of a composite function where the inner function is linear. We have derivative of the outer evaluated at the inner times the derivative of the inner. Now what just happened? Whoops. Let's try that again. Derivative of the outer, cosine. Derivative of the outer evaluated at the inner times derivative of the inner. Well, essentially all we ended up doing when we multiplied by the derivative of the inner was we multiplied by the constant here. The derivative of mx plus b is just m. We multiply by the constant. Well, isn't integration the reverse process of differentiation? So when we integrate, instead of multiplying by the derivative of this thing, we divide by the derivative of this thing. We don't have to use U-Substitution. So let's look at half a dozen examples just to make sure that we got it straight. And this will prevent us from having to use U-Substitution anytime we integrate a composite function whose inner function is linear. Here's a good one to start off with. This is a composite function. The outer function is e raised to the power of something. The inner function is 8x plus 2. The inner function is a linear function. So how do we integrate this? We take the integral of the outer function, evaluated at the inner function. And because the inner function is linear, we can just multiply by the derivative of the inner function. Now let's see, does that make sense? When we integrated, we divided by the derivative of this thing. We divided by 8. If we were computing the derivative of this thing, we'd write this thing down and multiply by the derivative of the inner. So yeah, that works. We integrate, it's the reverse process of differentiation. So instead of multiplying by the derivative of the inner, we divide by the derivative of the inner. Let's look at another example. It's a composite function. The inner function is linear. Oh, wait a minute, where's the constant term? Hey, this is the inner function. Mx plus b, b just happens to be 0, that's all. The inner function is linear. Okay, antiderivative of cosine is sine, evaluated at the inner. And now because this is integration and not differentiation, instead of multiplying by the derivative of the inner, we divide by the derivative of the inner. If we were computing the derivative, we'd multiply by 3. but we're computing the integral. We're doing the reverse process. We divide by the derivative of the integral. Looks good. The integral of sine of 8x plus 10 dx. The antiderivative of sine is negative cosine, evaluated at the inner function. And because we're integrating, instead of multiplying by the derivative of the inner, we divide by the derivative of the inner. Voila. Let's look at one that's slightly different. I think we've seen the number 8 a few too many times. This one will work. It's a function raised to a power. Compute the antiderivative of something raised to a power. We get something to the 11th power over 11, evaluated at the inner function. And now, because we're integrating and not differentiating, instead of multiplying by the derivative of the inner function, we divide by the derivative of the inner function. I may have been a little bit misleading at first. This doesn't work on every single kind of function that we're integrating where the inner function is a linear function. But it will work on exponentials where the inner function is linear, cosine where the inner function is linear, sine where the inner function is linear, functions raised to a power where the inner function is linear. So let's say, will it work for more than that? Let me just think about it for a second. You know, I guess we can stretch this a little bit. Let's try this one, okay? It's a composite function, and here's the inner function. Secant squared, since we have all of our integration formulas memorized, when we see secant squared, we go, aha, this is going to turn into tangent. Compute the antiderivative of secant squared, that's going to be tangent, evaluated at the inner function. And now, instead of, because we're integrating and not differentiating, instead of multiplying by the derivative of the inner, we divide by the derivative of the inner. Okay, so it will work on integrals that give us tangent, and by extension, cotangent. Okay. So tangent and cotangent, outer function, it works. What about this? When we see secant something, tangent something, all the flags should go up and say, you know what, we integrate this thing, we're going to get secant of something. The inner function appears twice, but that doesn't mean that it's not the inner function. So what do? We compute the derivative of the outer, secant of something, tangent of something. Evaluated at the inner. And now, because the inner function is linear, we can multiply by, let's see, what do we multiply by? If we were computing the derivative, we'd multiply by 3. But this is integration, it's the reverse process. So instead of multiplying by this 3, we're going to divide by 3. Holy moly. Wow, this works for a lot of things. Okay. Essentially, we can use this trick quite a bit. And as long as the inner function is linear, we don't really have to write out the U-substitution. Essentially, we write down the antiderivative of the outer, evaluated at the inner, and then just divide by the constant multiple of x. A nice shortcut to keep us from having to use U-substitution when we don't really have to. Now there's something else that I'd like to talk about as well when it comes to integrals. And this is not a secret that I'm about to tell you. It's just a review of things that we learned in Cal 2, but we probably didn't get a good handle on. And you know, I tell people in differential equations and also in calculus 2, we cover integration by parts and we cover partial fraction decomposition in calculus 2. But we don't really know integration by parts and we don't really know partial fraction decomposition until we've had differential equations. In differential equations, we will have ample opportunities to use both, and that's where we can really become experts on integration by parts and partial fraction decomposition. Here we go, a crash course in integration by parts. Here's the formula, integration by parts, and we should have this memorized. The integral of u dv equals uv minus the integral of v du. There's sort of a rhythm and rhyme melody kind of thing there. The integral of u dv is equal to uv minus the integral of v du. We need to have that memorized. And u is some function of x, and dv is some other function of x times dx. That's the way it works out. Now, how do we know if we have functions f of x and g of x, essentially? We have the product of two functions, f of x, g of x, times dx. How do we know which one is u and which one is going to be dv? And there are a couple of rules of thumb that we'll write down right off the bat. Okay, let u be the function whose derivative is simpler than the function itself. And let's take a monomial, x to the n. U prime, or the derivative of u, is nx to the n minus 1. We would consider this to be a simpler function than the original because it's a monomial of lower degree. And if we take a monomial like x to the n, where the exponent is a positive whole number, if we take a monomial and keep computing the derivative of it, eventually we're going to get a constant, and if we continue after that, we'll get 0. So looking at the big picture, a monomial is a function whose derivative, a monomial of lower degree, is simpler than the original function. So that's the classic case. We might also consider a polynomial to be a function whose derivative is simpler than itself. A polynomial of degree 3, its derivative is a polynomial of degree 2. We'd consider that to be a simpler function. Here's a classic example. U equals x, du dx equals 1. You can't get any simpler than that. Okay, so that's one rule of thumb. Another rule of thumb, let dv be the portion of the integral portion. I think I need to be more specific. The largest portion that we can integrate. Now, these rules of thumb are not foolproof, but 95% of the time they hold. Now let's see, why would we want dv to be the largest portion of the integral that we can integrate? Because to use this formula, we're going to take part of this integral and we're going to plug it into this formula. We're going to take dv, and in order to use this formula, we're going to have to be able to compute v. So it makes sense that dv would be the largest portion of the integral that we can integrate. So let's do a couple of examples before we look at some more rules of thumb. Here's a good example. X is a function whose derivative is simpler than itself. The derivative of x is 1. So we're probably going to let u equal x. And e to the x dx, we know how to integrate that. The integral of e to the x dx is just e to the x. And we consider e to the x to be a complicated function because it's a transcendental function. We can integrate this. This is the most complicated portion of the integral that we can integrate. So naturally, we're going to let dv equal e to the x dx. And that means if we integrate both sides, that v equals e to the x. And when we compute v, don't worry about the constant. The simplest antiderivative will always work when we're doing integration by parts. So forget the plus c for now. We'll throw on the plus c at the very end of the exercise, and that will work just fine. For right now, forget the plus c. We don't need it. Okay, u is equal to x. Du dx equals 1, which means du equals dx. Cool. Analyzing our integral, we have u dv. And since we know our integration by parts formula, we're going to write that formula down. The integral of u dv is equal to uv minus the integral of v du. And now we just fill in the blanks. U is x. V is e to the x. So here's uv minus the integral of v, which is e to the x, du, which is dx. Oh my goodness, it can't get any easier than this. The integral that we're left with is something that we can compute. Bingo, we're done. Okay, we'll do another one like this. Almost as simple, not quite, but almost. Let's go. X squared is a monomial. Its derivative is 2x. So we consider x squared to be a function whose derivative is simpler than the function itself. And that means we'll let u equal x squared. Sine of x dx, we know how to integrate that. And we'd say that sine of x dx is the most complicated portion of the integral that we know how to integrate. Well, let's see, we know how to integrate x squared, don't we? But sine of x dx is the most complicated portion of the integral that we know how to integrate. But we say that because sine of x is a transcendental function. It's more complicated than a monomial x squared. So we'll have dv equals sine of x dx. Du dx is 2x. Du is 2x dx. And what about these guys? We integrate to get v. The integral of dv, well, let's see. Maybe I should have said something about this in the last example. The integral of dv, if we insert a factor of 1 here, we're not changing the value of the integrand, are we? So we can think of this as 1 times dv, and the antiderivative of 1 with respect to v is just v plus some constant. And in the integration by parts process, we'll leave the constant off until the end. So we get v equals integral of sine x, that's negative cosine of x. And we'll do the plus c later. Okay. Let the good times roll. This is u times dv, and we're going to get uv minus the integral of v du. And now we just fill in the blanks. We get uv x squared times negative cosine of x minus the integral of v, which is negative cosine of x, v du, which is 2x dx. I don't know how to integrate that. Well, let's just tidy things up a bit. And you know what? I'm going to take this 2 and move it out in front of the integral sign. I'm going to have to use integration by parts again. And this leads us to the third rule of thumb. If we're doing more than one iteration of integration by parts, don't change horses in midstream. In other words, if u is the trig function the first time, let u be the trig function the second time. Now, I'm not saying that u is going to be the same trig function each time. But the first time, well, let's see, the first time, u was a monomial. So the second time, u should be a monomial also. The first time, dv was a trig function. So the second time, dv should be the trig function also. And what that means is I'm going to rewrite this. My monomial was u the first time. My monomial is going to be u the second time. My dv was a trig function the first time. My dv is going to be a trig function the second time. We're going to stick to that convention, because you know what happens if we don't? You know what happens if I let the trig function be u and the monomial be dv? In the second iteration of integration by parts, I'm just going to undo what it was the first time. I'm going to undo what I had done the first time using integration by parts, and I'm going to end up with this thing again. Don't want that to happen. So this is third rule of thumb. If we do integration by parts more than once, maintain our conventions. If u was the monomial the first time, let u be the monomial the second time. If the trig function was dv the first time, let the trig function be dv the second time. Very important rule of thumb. Okay, so u is going to be x, and dv is cosine of x dx. And that means that du dx is 1. Oh, I like that. And du is dx. We integrate over here. And v is going to be sine of x dx. Okay. So we get negative x squared cosine of x plus 2 integral of u dv. Don't forget this 2, which is 2 times uv minus the integral of v du. And that's going to be negative x squared cosine of x plus 2 times uv, x sine of x, okay? Minus the integral of v times du. V is sine of x dx, and du is just I'm sorry. Why didn't somebody stop me here? V is sine of x, period. Forgive me, please. Integral of v du is the integral of sine of x dx. And that's something we know how to compute. Two times x sine of dx minus 2 times the antiderivative of sine of x, which is negative cosine of x. No more integral, so I can add a plus c now. And I'll just tidy up what I have here with those 2 adjacent negative signs. Sometimes we will have to do the process more than once. The third rule of thumb tells us, don't switch roles of U and dV in midstream. So that was educational. Let's go a little bit further. Here's a good one. Our first rule of thumb would tell us to let x be u, or u to equal x. This is a function whose derivative is simpler than the function itself. And then dv would be the largest portion of the integral that we know how to integrate. Do we know how to integrate natural log of x? I'm assuming that we don't. So now we have a dv that we can't integrate. Here's where rule of thumb number 4 comes into play. Let u be the transcendental function. Oh, no, I'm not done yet. Whose derivative is algebraic. You know, we have some transcendental functions whose derivative is algebraic. Natural log of x, that's transcendental. We can't form this using a finite sequence of additions, subtractions, multiplications, exponentiations on x. So this is transcendental. Its derivative is algebraic. This can be formed by a finite sequence of additions, subtractions, multiplications, divisions. Let's see, what others do we know that are like this? Arc sine, transcendental, oh, by the way, these are not equal. This is the function, this is the derivative. Arc sine is transcendental. It has a derivative that's algebraic. And the same is true with all of the arc trig functions. So essentially, natural log and the arc trig functions, if we're doing integration by parts, we let those things be u. So here's our example. So this is our fourth rule of thumb. Let u be the transcendental function whose derivative is algebraic. Okay. So I'm going to have to rewrite this son of a gun. Here's my u, and here's dv. Oops. We got our u's, we got our v's. This is the integral of u dv. It's equal to uv minus the integral of v du. U is natural log of x. uv. V is 1/2 x squared. So uv minus the integral of v 1/2 x squared times du. Du is 1/x dx. Okay. I'm going to rearrange the order here. I'm going to write 1/2 x squared natural log of x minus 1/2. See, x squared times 1/x is just x. Okay, voila. Now I'll give you another example. I won't work it, but I'll tell you how to go about doing it. When I was doing this example, I mentioned that we didn't know what the antiderivative of natural log of x is. Can we really do integration by parts on that? We don't have a product, we just have natural log of x. And the answer is yes, we can. Because here's what we really have. Aha. Here's our other function. We let the transcendental function that has an algebraic derivative be u. And we let the rest of it be dv. Apply integration by parts to this thing, and you will get the antiderivative of natural log of x. This is a good one, and it will be a good introduction to our last rule of thumb. These things are both transcendental. Their derivatives are both transcendental. We each know how to integrate these things. And they have another unusual characteristic. Their derivatives are cyclic. If we compute the derivative of e to the x, we get e to the x. If we compute the derivative of e to the x again, we get e to the x again. The first, second, third, fourth, fifth, sixth, seventh, eighth derivatives of e to the x are all e to the x. It's a cycle of one. The nth derivative of e to the x is e to the x, and the n plus first derivative is going to be e to the x. Sine is also something that has a cyclic derivative, and depending on how we look at it, the cycle either has length 2 or length 4. We compute the derivative of sine of x, and we get cosine of x. And then we compute the derivative of cosine of x, and we get negative sine of x. So except for the negative sign out in front, we have the original function again. Now, if we want to split hairs, okay. We can take the derivative 2 more times, and we'll end up with positive sine of x. So depending on how we look at it, sine of x is a function whose derivative repeats either every 2 times or every 4 times that we compute the derivative. And the fact that both of these functions are cyclic with respect to their derivatives is going to have a major bearing on how integration by parts works here. As a matter of fact, when both functions are cyclic with respect to their derivatives, either one can be u, either one can be dv. And something very interesting is going to happen. We're going to have to do integration by parts at least twice, but something very interesting is going to happen. Let's check this out. We'll call this u. We'll call that dv. So here's u, there's dv. Don't do that. Okay, there we have it. We have the integral of u dv. This is going to give us uv minus the integral of v du. U is e to the x. V is negative cosine of x. Whoops. Minus the integral of v negative cosine of x du, which is e to the x dx. And remember my third rule of thumb? Don't switch horses in midstream. If u was the exponential function the first time around, then we're going to let u be the exponential function the second time around. And I'll put that first. And if the trig function was the dv the first time around, we're going to let the trig function be the dv the second time around. So u is still going to be e to the x. dv is going to be cosine of x dx. And look at what we get. We get negative e to the x cosine of x plus the integral of u dv, and that's going to be uv minus the integral of v du uv, that's e to the x sine x, minus the integral of v sine of x du, which is e to the x dx. And let me just rewrite what we have. And remember, we don't trade horses or switch horses in midstream. If the exponential function has been our u, it's going to continue to be our u. If the trig function has been our dv, it's going to continue to be our dv. And we look at what we have and we say, wait a minute, wait a minute. E to the x sine of x dx? That's what I was trying to compute in the first place. Oh, well, wait a minute, how did that happen? I didn't switch the roles of u and dv from one iteration to the next. So why is this happening? You're right. We didn't switch the roles of u and dv from the first iteration to the second iteration. So the fact that we ended up with the same integral that we started with is not our fault. We haven't done anything wrong. At this time, the best thing that we can do is just sit back and look at what it is that we've done. Here's where we started. I'm going to erase this. We're done with that. Here's what we've done. We started out with the integral of e to the x sine of x dx. And this is what we get. Negative e to the x cosine of x plus e to the x sine of x minus this piece of garbage, minus the integral of e to the x sine of x dx. This is what we've accomplished. We started out with this and we found out it's equal to this. And the thing that we're looking for is part of what we've generated, and we think that that's a horrible thing. We haven't done anything wrong. When we have the product of two functions that are both cyclic with respect to their derivatives, this is exactly what's supposed to happen. And think about it. What was it that we were trying to find in the first place? It was this, right? And now we have an equation that contains this expression. So let's not lose sight of what we wanted. That's what we're looking for. If we're trying to solve for x and we see x in two different parts of an equation, we go, there's an x here and there's an x there. Oh, I can't find x. No, we solve for it algebraically. This is great news here. We have an equation that contains exactly what we want. If we're looking for x and we have x in two different parts of the equation, what do? Don't we move the x's to one side of the equation and everything else to the other side of the equation? Well, here's our x, the integral of e to the x sine of x. That's what we're looking for. So we're going to move this to the other side. We're going to add the integral of e to the x sine of x dx to both sides of the equation. And oh, this is not bad news, this is great news. So now we have 2 times the integral of e to the x sine of x dx equals this garbage. So what do we do now? Just divide both sides by that 2, right? You've got it. You've got it. Whoops, whoops, whoops. I did say divide both sides by 2, didn't I? Let's see if I understand what the word both means. And now to wrap it up in a nice wrapper and put a nice bow on it, we'll just add the plus c. This happens every time we're integrating the product of two functions that are cyclic with respect to their own derivatives. This is a good one to do. Guess what? E to the x cosine of x works exactly the same way.